point a good telescope at almost any patch of night sky, and every galaxy that comes into focus, along with the Milky Way itself, the Sun and the Earth beneath your feet, belongs to a single structure roughly 500 million light-years across. It was mapped for the first time only in 2014, and given a name that means immense heaven. It is called Laniakea, and it contains something on the order of 100,000 galaxies, all of them drifting together along invisible rivers of gravity toward one low point in space, the way water finds its way downhill toward a river basin. Nobody suspected a structure this size existed for most of the history of astronomy. Because it cannot be photographed and it cannot be seen by eye, no matter how dark the sky or how large the telescope pointed at it, it had to be measured one galaxy's motion at a time across decades of patient work. What follows traces that measurement outward from Earth's own small neighborhood to the edge of the supercluster we actually live inside, and toward an answer that turns out not to be a boundary at all, but something far stranger. Light leaves the Sun and reaches Earth in about 8 minutes. It reaches Neptune, the outermost planet, in roughly 4 hours. Past Neptune, the solar system does not simply stop. It thins into the Kuiper belt, a broad disk of icy bodies that includes Pluto, and beyond that into the Oort cloud, a vast spherical shell of comets so distant that light takes more than a year to reach even its inner edge, and far longer to reach its outer one. The outer Oort cloud sits somewhere on the order of 100,000 times farther from the Sun than Earth does. Some comets that visit the inner solar system only once every few thousand years begin their long fall from deep within that distant shell, nudged loose by the faint gravity of a passing star far beyond the reach of the Sun's own light. That distance, difficult as it already is to hold in the mind, turns out to be only the first step of a much longer answer to the question of where we actually are. Step back far enough and the Sun itself stops being a place with planets around it, and becomes what it truly is to the rest of the universe. One ordinary star, a single pale point of light indistinguishable from millions of others in a photograph of the right patch of sky. It carries 8 planets, dozens of moons, and countless comets and asteroids, and every one of them together adds up to a rounding error next to the star at the center. The Sun alone holds more than 99.8% of all the mass in the solar system. On the scale of what comes next, though, even the Sun quickly disappears into the crowd. Astronomers did not always know even this much. 200 years ago, the shape of our galaxy was little more than a guess, built from counting how many stars appeared in different directions of the sky. It took the discovery of a class of pulsing stars called Cepheid variables, whose brightness rises and falls at a rate directly tied to how much light they truly put out, to give astronomers a reliable ruler for cosmic distances. Using that ruler in 1918, the astronomer Harlow Shapley placed the Sun far out in the disk of the galaxy rather than at its center, and that single correction quietly ended thousands of years of assuming Earth's neighborhood sat at the middle of everything. The Sun sits inside a galaxy so large that light, moving at about 300,000 kilometers every second, needs roughly 100,000 years to cross it from one edge to the other. That galaxy holds something on the order of 100 billion to 400 billion stars. And the Sun is a completely unremarkable member of it, about 2/3 of the way out from the center toward the disk's ragged edge. Nothing about the Sun's position is special. It is not near the crowded core, and it is not at the outer fringe. It simply sits inside one of the disk's spiral arms, a modest resident of a modest suburb. A useful way to hold this jump in scale in mind. If the distance from the Sun to Neptune were shrunk down to the width of a dinner plate, the outer edge of the Oort cloud, on that same shrunken scale, would sit roughly 2 kilometers away, and the galaxy that contains all of it, on that same shrunken scale, would stretch farther than the distance from Earth to the Moon. Each step outward does not simply add distance to the last one. It multiplies it, adding an entire additional order of magnitude every time the frame widens. None of the material out at those distances is crowded together the way an artist's illustration might suggest. The icy bodies of the Kuiper belt, like the rocky ones in the inner asteroid belt closer to the Sun, are spread across such enormous volumes of space that spacecraft have crossed both without any realistic risk of a collision. A probe launched toward Pluto and beyond passed straight through the Kuiper belt without incident, not because it was lucky, but because there was essentially nothing in its way to hit. Emptiness, not crowding, is the normal condition of space at every scale that follows. The Voyager 1 probe, launched in 1977, and now the most distant human-made object, has spent decades crossing this same emptiness and only recently passed beyond the Sun's direct influence into interstellar space, without ever coming close to another body along the way. That larger pattern begins with the galaxy's own true shape, and with a question that puzzled astronomers for most of the 20th century. Which direction is the centre? How far away is it? And what does the rest of the disk actually look like from the outside? Answering it required looking past the Sun's own neighbourhood entirely, and asking what kind of structure this galaxy really is. From the outside, if such a view were possible, the Milky Way would look like a flattened pinwheel of light, a bright central bulge of old densely packed stars, surrounded by a thin disk marked with sweeping spiral arms of gas, dust and newly forming stars, the whole thing wrapped in a faint, roughly spherical halo of ancient stars and dense star clusters far older than the disk itself. The disk spans somewhere on the order of 100,000 to 120,000 light-years, though its edge is not a hard line. The density of stars simply fades out gradually, the way a city's lights thin into farmland rather than stopping at a wall. The Sun sits about 26,000 light-years from the galaxy's centre, inside a minor spiral structure called the Orion Arm, a spur that branches off between two of the galaxy's larger arms, rather than sitting on one of the grand spiral features itself. From this vantage point, roughly 2/3 of the way out toward the edge, the galaxy's brightest core is not even visible to the eye. Thick lanes of interstellar dust block that light almost completely, which is part of why it took so long for astronomers to work out the galaxy's true shape from the inside. The Sun is moving as it orbits, carrying Earth and the rest of the solar system with it, at roughly 220 kilometers every second, fast enough to cross the distance from London to New York in well under a minute. Even at that speed, one full orbit of the galactic center takes the Sun somewhere around 230 million years, a span of time sometimes called a galactic year. Since the Sun and Earth formed about 4.6 billion years ago, the solar system has completed only about 20 such orbits in its entire existence. The dinosaurs went extinct roughly a quarter of a galactic year ago. Complex animal life on Earth is only a few galactic years old. At the exact center of all this motion sits an object astronomers call Sagittarius A star, a supermassive black hole with a mass estimated at roughly 4 million times that of the Sun. It is not, contrary to a common misconception about black holes generally, some kind of cosmic vacuum cleaner reaching out and swallowing everything nearby. Stars and gas clouds well outside its immediate vicinity orbit it the same way any object orbits any other mass, following stable paths that have persisted for billions of years. It anchors the galaxy's rotation gravitationally, the way the Sun anchors the planets, without consuming the disk around it. The spiral arms themselves are not fixed structures made of the same stars forever, the way ribs are fixed to a skeleton. They are better understood as density waves, regions where gas is compressed enough to trigger bursts of new star formation, moving through the disk, somewhat independently of the stars that pass through them. The way a traffic jam can persist on a highway even as individual cars enter and leave it. That is why spiral arms glow brightly with young, hot blue stars and pink clouds of ionized hydrogen. They mark where star formation is happening right now, not where the galaxy's oldest material happens to sit. Measuring all of this from inside the disk required a specific and clever trick, the same kind of trick that will prove useful again at a much larger scale still to come. Astronomers track objects of known, calibrated brightness, called standard candles, and compare how bright those objects actually appear to how bright they should appear at a given distance. Cepheid variable stars, and later entire classes of exploding stars called supernovae, filled that role, turning apparent brightness into a genuine ruler for the universe. The Milky Way, for all its scale, is not an isolated island. It has close neighbours of its own, bound to it by gravity, orbiting it and being orbited in turn, forming a small cluster of galaxies that astronomers call the local group. Understanding that group, and one galaxy in particular headed on a slow collision course with our own, is the next step outward in mapping our true address. The Milky Way's nearest large neighbour is the Andromeda Galaxy, a spiral roughly comparable in size and visible, on a clear dark night far from city lights, as a faint smudge to the naked eye, even though it sits about 2.5 million light-years away. That single fact is worth sitting with. The light entering your eye from Andromeda left it 2.5 million years ago, well before modern humans existed, and has been travelling through empty space ever since, at 300,000 kilometres every second, without slowing down at all. Andromeda and the Milky Way are not simply neighbours passing at a distance. They are gravitationally bound to each other, along with roughly 80 smaller galaxies, in a loose structure astronomers call the local group, spanning something on the order of 10 million light-years across. Most of that group's members are small, faint dwarf galaxies, many of them satellites of either the Milky Way or Andromeda, the way moons orbit planets, though on a far larger scale, and made of hundreds of millions of stars rather than solid rock. Andromeda is currently moving toward the Milky Way at roughly 110 kilometers every second, and based on decades of measurements of its motion, astronomers predict the two galaxies will begin to merge in roughly 4 to 5 billion years, an event sometimes given the name Milkomeda for the combined galaxy that would eventually result. This is not expected to be a violent collision in the way two solid objects colliding would be. Galaxies are made almost entirely of empty space between stars. When Andromeda and the Milky Way pass through each other, the overwhelming likelihood is that not a single star will directly strike another. Gravity will reshape both galaxies over hundreds of millions of years, flinging some stars into long tidal streams and eventually settling into one larger elliptical galaxy without a single collision between two suns. A useful comparison for that timescale. 4 billion years ago, life on Earth had not yet developed the ability to breathe oxygen, and the continents had barely begun forming their modern shapes. The merger of Andromeda and the Milky Way sits about that far in the other direction, into the future, a span so long that predicting exactly what form of life, if any, might still exist on Earth to witness, it is well beyond what current science can responsibly claim. The local group itself is dominated gravitationally by its two largest members, Andromeda and the Milky Way, each anchoring roughly half the group's total mass between them. Everything else, dozens of smaller dwarf galaxies with names like the Small and Large Magellanic Clouds, the Triangulum Galaxy, and many fainter systems too dim to see without a large telescope, orbits within the gravitational field those two giants create together. It is a small neighbourhood by the standards of what comes next, but it already stretches far beyond anything the unaided human eye, or even most amateur telescopes, can meaningfully resolve into individual stars. Even a structure 10 million light-years across, however, is not the largest unit astronomers use to describe where a galaxy lives. Groups like the local group are themselves drawn toward larger concentrations of mass nearby, in the same way a small town's roads eventually feed into a larger regional highway system. The nearest such concentration is a genuine giant, a cluster of well over 1,000 galaxies, whose gravity is strong enough to be measurably slowing the expansion of the local group itself. Galaxies almost never sit alone. They gather into groups like the local group, and groups themselves gather into far larger structures called clusters, some containing not dozens but thousands of individual galaxies bound together by gravity. The nearest large one to us is the Virgo cluster, roughly 54 million light-years away, home to well over 1,000 galaxies, and possibly closer to 2,000 once the faintest dwarf members are counted. Virgo is massive enough that its gravity reaches out well beyond its own visible boundary, and measurably affects its neighbours. The overall universe is expanding, meaning that on average, distant galaxies are moving apart from each other as space itself stretches between them. A discovery credited to the astronomer Edwin Hubble in the 1920s. But gravity can locally push back against that expansion, and Virgo's mass is doing exactly that to the local group, rather than drifting away from Virgo at the full rate the expanding universe would otherwise predict. The local group is being gravitationally slowed down, pulled very slightly back in Virgo's direction, a measurable tug across 54 million light-years of otherwise empty space. This nesting pattern, groups inside clusters, is not a coincidence of a few nearby examples. It is how matter organizes itself at every scale astronomers have been able to map. Individual stars gather into galaxies gather into groups gather into clusters, and clusters, it turns out, gather into something larger still, loose associations spanning hundreds of millions of light-years, which astronomers eventually came to call superclusters. The word itself was in use for decades before anyone had a reliable way to say where one supercluster ended and the next one began. For most of the 20th century, astronomers defined these structures the same way they defined everything smaller, by counting galaxies and looking for regions where they were unusually dense, clustered more tightly together than the average patch of sky. Under that definition, the local group, the Milky Way, Andromeda, and the Virgo cluster together were said to belong to something called the Virgo supercluster, or sometimes the local supercluster, a structure roughly 110 million light-years across, containing on the order of 100 galaxy groups and clusters. That definition, built purely on where galaxies happen to sit, worked reasonably well as a first approximation, but it had a fundamental limitation that would not become clear until decades later. Counting galaxies tells you where matter is right now. It does not tell you where that matter is actually going, or what larger structure it is truly part of, because galaxies at the ragged edge of one density-defined supercluster can easily be gravitationally bound to and heading toward an entirely different structure than the map suggested. An analogy from familiar geography helps here. Imagine trying to draw the borders of a watershed, the total area of land whose rainfall eventually drains into a single river, using only a map of population density. Some towns near the edge of one watershed might sit closer, as the crow flies, to the towns of a neighbouring watershed, even though their rainfall flows in a completely different direction. Population density on its own cannot tell you which way the water actually runs. For decades, astronomers were mapping the galactic equivalent of population density without a reliable way to measure the equivalent of the water flowing beneath it. Solving that problem meant asking a different, harder question about every galaxy in reach. Not simply where is it, but which way and how fast is it actually moving. Answering that question would eventually overturn the old, density-based map of our supercluster entirely, and it began with a stubborn anomaly that astronomers first noticed in the late 1970s. Entire regions of the sky where galaxies seemed to be moving in ways the expanding universe alone could not explain. Every galaxy's light carries a signature of its motion, encoded in a phenomenon called redshift. As a galaxy moves away from an observer, the light it emits stretches to longer, redder wavelengths, in the same way a passing ambulance's siren drops in pitch as it moves away from a listener. Because the universe as a whole is expanding, almost every distant galaxy shows this redshift, and the amount of stretching, on average, tells astronomers roughly how far away that galaxy is. More distant galaxies are, on average, moving away faster, and therefore show a larger redshift, a relationship first established by Edwin Hubble and now called Hubble's law. The key phrase there is on average. Individual galaxies do not follow the smooth mathematical expansion of the universe perfectly. Nearby mass concentrations, clusters and superclusters, exert their own gravitational pull, adding a small extra motion on top of the overall expansion, called a peculiar velocity. A galaxy sitting near a massive cluster might show a redshift slightly smaller or larger than its true distance alone would predict, because part of its measured motion is genuine expansion, and part of it is gravity pulling it toward, or letting it drift past, a nearby concentration of mass. In the late 1970s and through the 1980s, a group of astronomers, including Sandra Faber, Alan Dressler, and several collaborators, who became known informally as the Seven Samurai, began carefully measuring these peculiar velocities across a large sample of galaxies, including our own local group. What they found was strange. The Milky Way, Andromeda, the entire local group, and thousands of other galaxies across an enormous stretch of sky were all showing a peculiar velocity in the same general direction, as though something massive, well beyond the Virgo cluster, was pulling on all of them at once. They nicknamed the source of that pull the Great Attractor. Its estimated mass was staggering, on early estimates equivalent to tens of thousands of galaxies concentrated in one region, though later, more careful measurements substantially revised that figure downward. Its exact location was maddeningly difficult to pin down, because it sat, from Earth's vantage point, almost directly behind the crowded, dust-choked plain of the Milky Way itself, a region of sky so obscured by our own galaxy, stars and dust that astronomers had nicknamed it the zone of avoidance for exactly this reason. Almost nothing behind it can be seen in visible light. Only by switching to other kinds of observation, including radio waves and X-rays that can pass through interstellar dust far more easily than visible light, were astronomers eventually able to confirm what lay behind the obscuring dust. A real dense concentration of galaxies, centered roughly in the direction of the constellations Centaurus and Norma, somewhere on the order of 150 million to 250 million light-years away. It was not a single monstrous object, but a genuine cluster of galaxies, among the densest known in the relatively nearby universe, sitting at the bottom of an enormous gravitational valley that the entire local group, it turned out, had been sliding down for billions of years without anyone noticing. The discovery of the Great Attractor was the first solid evidence that the old density-based map of our supercluster was missing something essential. Astronomers were no longer just asking where the galaxies were. They were beginning for the first time to ask where they were all going, and the answer pointed toward a single shared direction, spanning a volume of space far larger than the Virgo supercluster's old density-defined boundary had ever suggested. Answering that question properly, for every galaxy within reach rather than just a sample of a few thousand, would take decades more work, an enormous international survey effort, and a fundamentally new way of drawing a supercluster's borders altogether. Confirming the Great Attractor's pull across a handful of galaxies was one thing. Mapping the true motion of every galaxy across hundreds of millions of light-years, well enough to trace the actual shape of the gravitational landscape they were all sliding through, was a far larger undertaking, and it required solving a specific technical problem first, telling the difference for any given galaxy between how far away it truly is and how fast the expanding universe alone would predict it to be moving. Redshift alone cannot do this because it measures a galaxy's total velocity, expansion plus peculiar motion combined, without separating the two. What astronomers needed was an independent way to measure a galaxy's true distance, something that did not rely on redshift at all, so that the two numbers could be compared and the leftover difference, the peculiar velocity, could be isolated. The tool that made this possible at a large scale is called the Tully-Fisher relation, developed in the 1970s by the astronomer R. Brent Tully and his collaborator J. Richard Fisher. The Tully-Fisher relation exploits a reliable pattern in spiral galaxies. The faster a spiral galaxy rotates, which can be measured directly from the motion of its gas, the more massive and therefore the more intrinsically luminous that galaxy tends to be. Measure a galaxy's rotation speed, and you can predict how bright it truly is. Compare that predicted true brightness to how bright it actually appears from Earth, dimmed by distance the same way a lamp looks fainter the farther away it sits, and you can calculate a genuine, redshift-independent distance to that galaxy. With that tool in hand, Tully spent decades leading an ever-expanding international collaboration to apply it, galaxy by galaxy, across as much of the observable universe as telescopes could reach. The resulting project, named Cosmic Flows, eventually measured reliable distances and true peculiar velocities for tens of thousands of galaxies, the largest catalogue of its kind ever compiled, refined across 3 major published releases between the early 2000s and the 2010s, with contributions from a large international team, including the French astronomer Hélène Courtois. What emerged from that catalogue was not a simple list of positions. It was something closer to a weather map, but for gravity instead of wind. A 3-dimensional field showing, for tens of thousands of points across a vast volume of space, not just where each galaxy sat, but which direction and how fast it was truly moving once the universe's overall expansion had been subtracted out. Regions where many neighbouring galaxies all showed peculiar velocities pointing the same way marked the slopes of enormous, invisible gravitational valleys. Regions where velocities diverged, pointing away from each other in different directions, marked the ridgelines, the ill-defined high ground between one valley and the next. A useful comparison for what this map actually resembles. Picture a satellite photograph of a continent showing every raindrop's path rather than the shape of the land itself, tracing exactly which valley each drop eventually drains into. Nowhere on such a map is there a fence or a wall marking one watershed's edge. There is only a ridge, a place where 2 neighbouring slopes meet and rainfall on one side flows one way, while rainfall a few meters over flows the opposite way. Tully and his collaborators realized that galaxy-peculiar velocities behaved exactly the same way, and that this, rather than raw galaxy density, was the physically correct way to define a supercluster's true boundary. Applying that watershed logic to the full Cosmic Flows catalogue of tens of thousands of galaxies was a substantial computational undertaking of its own, one that would finally answer the question the Great Attractor had first raised decades earlier, not simply that the local group was being pulled somewhere, but the complete shape, extent, and true membership of the entire gravitational basin it belonged to. In September 2014, R. Brent Tully, Hélène Courtois, and their collaborators published the results of that watershed analysis in the journal Nature. Rather than drawing supercluster boundaries around regions of high galaxy density, as every previous map had done, they drew them around complete gravitational drainage basins. Every galaxy whose measured peculiar velocity flowed, even indirectly, toward the same central region, regardless of how sparsely or densely packed the galaxies along the way happened to be. The result reshaped the map of our cosmic neighborhood. The old Virgo supercluster, roughly 110 million light-years across, turned out to be only the near edge of something dramatically larger, a single connected gravitational basin roughly 500 million light-years across, containing an estimated 100,000 galaxies and a combined mass on the order of 100,000 trillion times the mass of the Sun, or roughly 100,000 times the mass of the Milky Way alone. Every galaxy within that basin, including the Milky Way, Andromeda, the entire local group and the Virgo cluster, all shared a peculiar velocity pointing, eventually, in the same general direction. Toward the great attractor, which the new map confirmed sat not at the edge of this structure but very close to the center of its gravitational basin. The team gave the new supercluster a name drawn from Hawaiian language rather than the usual practice of naming a structure after a constellation or a lead researcher. Laniakea, meaning immense heaven or immeasurable heaven, chosen partly in honor of Hawaii's own deep tradition of ocean navigation by the stars, and partly because the astronomers involved, several of whom worked at Hawaii's astronomical observatories, wanted a name that captured the scale of what they had found without borrowing the usual dry catalogue designation. To grasp just how large a jump this represented from the old picture, consider the comparison directly. The local group, at roughly 10 million light-years across, sits inside the Virgo cluster's gravitational reach, at roughly 54 million light-years away. The old Virgo supercluster spanned roughly 110 million light-years, and Laniakea, the structure that finally emerged from tracing actual galaxy motion rather than galaxy density, spans roughly 500 million light-years, nearly 5 times larger than the density-based map it replaced. Each of those earlier maps was not wrong, exactly. They were each accurate descriptions of a smaller piece of a much larger picture that nobody had yet found the right method to see whole. Laniakea's total galaxy count, roughly 100,000, dwarfs the roughly 100 or so galaxy groups and clusters that made up the old Virgo supercluster definition, though most of Laniakea's galaxies are relatively faint, gathered into filaments and sheets of only modest density, rather than concentrated in a small number of giant clusters. The Virgo cluster remains the largest single concentration of mass inside Laniakea that is close enough to us to study in detail. The Great Attractor's Norma cluster and the surrounding Centaurus region sit closer still to the structure's actual gravitational center. The 2014 paper did something else worth noting for how science actually progresses. It did not claim to have found the largest structure the universe contains, and it explicitly acknowledged the limits of its own method. The watershed analysis could only trace flows within the range, where cosmic flows had reliable galaxy distance measurements, meaning Laniakea's boundary, wherever the data ran out, was necessarily somewhat uncertain, an edge drawn at the limit of what could be confidently measured rather than a true physical wall. That honest limitation would matter again. Years later, when improved data began to suggest the boundary might need to be redrawn. For now, though, the discovery answered a fundamental question. Laniakea is the name for the complete gravitational basin the Milky Way belongs to, a single flow of 100,000 galaxies all sliding, however slowly, toward the same low point in space. What remained was to work out exactly where, within that vast basin, our own galaxy actually sits. Discovering that we belong to Laniakea did not place us at its center, quite the opposite. The Milky Way, along with the rest of the local group, sits well out toward the edge of the basin, in a relatively sparse region of galaxy filaments, sometimes called the local sheet, a flattened arrangement of galaxies including the local group and several neighboring groups, all moving together in roughly the same direction. The Great Attractor's dense concentration of galaxies, near the true gravitational center of Laniakea, lies on the order of 150 million to 250 million light-years from us, meaning we are located far closer to Laniakea's outer boundary than to its heart. This is a familiar pattern by now, repeating at yet another scale. The Sun is not at the center of the Milky Way. The Milky Way is not the dominant galaxy of the local group, sharing that role roughly equally with Andromeda. The local group is not at the center of the Virgo cluster's gravitational reach, sitting instead at its outer edge, and now the entire local group turns out to occupy an unremarkable outer filament of Laniakea rather than anything resembling a central position. At every scale from the Sun outward, our dress has turned out to be ordinary, ranging from modest to peripheral, never central. Between the local group and the Great Attractor's dense core lies the Virgo cluster, which the Laniakea map revealed to be functioning as something like a regional hub within the larger basin, a substantial mass concentration positioned along one of the major channels of galaxy flow, gathering material from the surrounding filaments before that material continues onward, eventually toward the deeper gravitational valley at Laniakea's center. Virgo is large enough on its own to noticeably bend the paths of galaxies flowing past it, the same way a large boulder in a stream diverts and slows the water passing around it without stopping the stream's overall downhill flow. Mapping this three-dimensional structure required more than measuring speeds along a single line of sight from Earth. It required determining the full direction of each galaxy's peculiar velocity in 3 dimensions, a task considerably harder than measuring redshift alone, since redshift only ever reveals motion directly toward or away from us, never sideways motion across the sky. Tully's team achieved this by comparing peculiar velocities across enormous numbers of neighboring galaxies simultaneously, using the consistency or inconsistency of their combined motions to triangulate the true 3-dimensional flow field, filament by filament, the same way a meteorologist reconstructs wind direction across a whole continent from many individual local wind readings rather than a single one. The resulting picture of Laniakea's internal structure looks less like a solid ball of galaxies, and more like a loose 3-dimensional network of filaments and sheets, connected across enormous voids of near-empty space, all draining, eventually and unevenly, toward the Great Attractor region. Some filaments carry a relatively dense, well-populated flow of galaxies. Others, including the one containing the local group, are comparatively sparse, threading through large volumes where galaxies are few and far between. The overall shape resembles, more than anything else, a river delta viewed from above. If a river delta could somehow exist in 3 dimensions and span 500 million light-years, that filament we call home eventually feeds toward Virgo and from there deeper into Laniakea's interior, but the actual pull the local group feels from the Great Attractor's direction is a relatively gentle one compared to the much stronger local gravity binding the Milky Way and Andromeda to each other. We are participants in Laniakea's slow overall drift, but we are not being drawn toward it aggressively. The entire journey, if it can even be called a journey, unfolds across timescales far longer than the current age of the universe itself allows anyone to observe directly. That journey will likely never actually be completed, because Laniakea is not just a static map but a structure with a fate, one that hinges on a force no measurement of galaxy motion alone, however patient or precise, was ever designed to detect. At the heart of the Great Attractor's dense region sits a real catalogued galaxy cluster called the Norma Cluster, also known by its catalogue designation ABEL 3627, one of the more massive clusters known within a few 100 million light-years of Earth. It was long obscured almost entirely by the Milky Way's own dust and stars, sitting nearly behind the galactic plane from our point of view, and it took observations in radio waves and X-rays, which passed through dust far more easily than visible light, to finally confirm it as a genuine, richly populated cluster rather than an inferred mass with no visible source. The Norma cluster alone, however, does not fully account for the total pull that the original Great Attractor measurements detected across such an enormous span of sky. So, once astronomers had better distance measurements and could trace peculiar velocities out even farther than the original cosmic flow's survey reached, they found something that at first seemed to complicate the tidy picture Laniakea had just established, an even larger concentration of galaxy clusters, called the Shapley concentration, sitting roughly 650 million light-years away, well beyond Laniakea's own boundary, in nearly the same general direction as the Great Attractor as seen from Earth. The Shapley concentration, named for the astronomer Harlow Shapley, who first noted an unusual density of galaxies in that direction decades earlier, is thought to be one of the most massive structures in the relatively nearby universe, containing dozens of galaxy clusters in a comparatively compact region. Because it lies almost directly behind the Great Attractor from Earth's vantage point, for years astronomers debated how much of the peculiar velocity they were measuring locally was due to the nearby Great Attractor itself, and how much was actually a much weaker but still measurable tug from the far more massive Shapley concentration lying beyond it, like 2 lamps positioned nearly in line, so that it becomes difficult to tell how much of the light reaching you comes from the near one and how much from the far one. Current evidence, according to researchers working on this problem, suggests both are real contributors. The Great Attractor's Norma cluster region genuinely does dominate the local peculiar velocity field that defines Laniakea's basin, while the Shapley concentration exerts a real but comparatively smaller additional pull, one strong enough to be measurable across hundreds of millions of light years, but not strong enough to redirect Laniakea's overall internal flow away from its own gravitational center. This matters for a subtle but important reason. Laniakea itself, as a whole structure, is not simply sitting still relative to the rest of the universe. The same watershed logic that revealed our galaxy's motion toward the Great Attractor also implies that Laniakea's center of mass, the Great Attractor region, is itself drifting gently toward the Shapley concentration in the same way a river's local eddies can each swirl in their own direction even while the entire river continues flowing toward the sea. Structure, at this scale, keeps nesting inside larger structure, seemingly without an obvious final stopping point. A rough sense of the numbers involved. If the Milky Way's gravitational influence on a nearby dwarf galaxy is a firm handshake, and the Virgo cluster's influence on the local group is a strong ocean current, then the Great Attractor's influence on the entire local sheet is closer to the pull of a distant but genuine gravitational field, and the Shapley concentration's influence on the Great Attractor itself is fainter again. A whisper of gravity across hundreds of millions of light years, but a whisper current instruments can still detect and measure with confidence. Whether this nesting pattern of ever larger, ever fainter gravitational pulls eventually terminates in some single largest structure, or simply continues indefinitely at ever weaker strength across the observable universe, is a genuinely open question in cosmology today. What is not in doubt, however, is a separate and in some ways more consequential fact about Laniakea's future. Unlike the Milky Way, unlike the local group, and unlike the Virgo cluster, Laniakea itself is not gravitationally bound together as a single unit, and that distinction turns out to define its entire ultimate fate. A galaxy is gravitationally bound. Its stars will never drift apart on their own, because the mutual gravity holding them together is stronger than any force trying to pull them apart. The local group, similarly, is gravitationally bound. The Milky Way and Andromeda are approaching each other, not receding, because their mutual gravity has already overcome the overall expansion of the universe at that comparatively short range. Even the Virgo cluster, at 54 million light-years, remains gravitationally bound as a whole, its member galaxies orbiting a shared center of mass rather than drifting apart. Laniakea is different, and this difference is central to what kind of structure it actually is. It was never defined by gravitational binding in the first place. It was defined by shared direction of peculiar velocity, a watershed of galaxies all currently flowing the same general way. Many regions within Laniakea, including the local group and the Virgo cluster, are themselves gravitationally bound at their own smallest scale. But the full half-billion light-year basin as a whole is not bound together the way a single galaxy or a single cluster is. Its galaxies are moving toward a shared gravitational low point, but not fast enough, and not with strong enough mutual gravity across such vast distances, to ever fully collapse into one bound supercluster. This distinction becomes critical once dark energy enters the picture. Since the late 1990s, observations of distant exploding stars called Type Ia supernovae, another kind of reliable standard candle, revealed that the expansion of the universe is not merely continuing, but accelerating, driven by a poorly understood phenomenon researchers call dark energy, which appears to make up roughly 68% of the total energy content of the universe. On small scales where gravity is strong, like within a galaxy or even within the local group, dark energy's effect is utterly negligible next to the pull of ordinary gravity. But on the scale of hundreds of millions of light-years, where gravity's pull between one filament of galaxies and another is already comparatively weak, the accelerating expansion driven by dark energy becomes significant and eventually decisive. Based on current models of that accelerating expansion, researchers who study large-scale structure predict that Laniakea's constituent groups and clusters, while remaining bound and intact themselves, will gradually stop responding meaningfully to each other's gravity at all. The overall flow that currently defines Laniakea as a single connected watershed will weaken over time, and eventually the accelerating stretch of space between the filaments is expected to overwhelm what gravitational pull remains between them. Over a timescale on the order of tens of billions of years, far longer than the roughly 13.8 billion years the universe has existed. Laniakea as a single coherent flow is expected to effectively cease to exist, even though every galaxy currently within it, and every cluster and group of galaxies inside it, will remain fully intact on their own. This is not a unique fate reserved for Laniakea. It is, according to current cosmological models, the eventual fate of every supercluster-scale structure in the universe, a consequence built into dark energy's accelerating push rather than anything particular to our own neighborhood. Superclusters, unlike the galaxies and clusters that make them up, may simply be a transient feature of a particular era in cosmic history, structures that can be identified and mapped now, while enough time remains for their gravity to still show up in the pattern of galaxy motion, but that will not persist as a connected whole into the universe's much longer future. There is a genuine irony worth sitting with here. The very technique that finally allowed astronomers to identify Laniakea, tracing tiny, patient measurements of peculiar velocity across 100,000 galaxies, only works because the structure has not yet been fully pulled apart by the same accelerating expansion that will eventually erase it. Laniakea was mapped in a real sense, near the tail end of the window in which such a map could still be drawn at all. Future civilizations, tens of billions of years from now, looking outward from wherever the Milky Way's remnants happen to be by then, would find no comparable watershed left to measure. None of this makes Laniakea, or the effort spent finding it, any less real or any less significant right now. It simply means that Laniakea belongs to a category of structure fundamentally different from a galaxy or a cluster, not a permanent object, but a temporary pattern of shared motion, visible for a finite window in cosmic history, of which the present moment happens to be a part. Understanding just how unusual, or how ordinary, that pattern is required comparing Laniakea to its neighbours, the other superclusters mapped using the very same watershed method. Once astronomers had a reliable, physically grounded method for defining a supercluster by tracing galaxy flows rather than counting density, the same technique could be applied to other regions of the observable universe, and it revealed that Laniakea, despite its genuinely enormous size, is far from the largest structure of its kind. On the same rough scale sits the Perseus-Pisces supercluster, a long filament-like structure spanning several 100 million light-years, and the Coma supercluster, both catalogued well before Laniakea using older, density-based methods, and both later analysed with velocity data of their own. Far larger than any of these, and larger even than the Shapley concentration, whose gravity tugs steadily at Laniakea's own centre of mass from farther out still, are structures that push the very definition of what counts as a single object. The Hercules Corona Borealis Great Wall, identified through a survey of extremely distant gamma-ray bursts in 2013, appears to span something on the order of 10 billion light-years, an almost unbelievable fraction of the entire observable universe, which itself has a diameter of roughly 93 billion light-years. Structures at that scale remain genuinely controversial among cosmologists, since current models of how the universe evolved suggest that structures should not be able to grow coherently much beyond roughly 1 billion light-years within the time the universe has existed. Some researchers argue these enormous claimed walls may be partly an effect of how the survey data was gathered, rather than a single physically connected structure, in the way Laniakea's galaxies are connected by measured, coherent flow. A more solidly established comparison is the Sloan Great Wall, discovered in 2003 using the Sloan Digital Sky Survey, spanning roughly 1.4 billion light-years, and later structures identified in even larger surveys, including one sometimes called the South Pole Wall, discovered in 2020 using much the same flow-tracing philosophy Tully pioneered with Laniakea, stretching across more than 1 billion light-years and, remarkably, gravitationally influencing the motion of galaxies as close to us as our own local group, in a direction almost opposite to the pull of the Great Attractor. Set against structures on that scale, Laniakea's roughly 500 million light-years and 100,000 galaxies represent a genuinely large, but by no means extreme example of what the universe is capable of assembling through gravity alone. It sits comfortably in the middle range of known supercluster-scale structures, larger than smaller, more isolated superclusters, but a small fraction of the size of the very largest walls and filaments cosmologists have identified using similar flow and density surveys across the full observable universe. This places Laniakea's true significance in a clearer light. Its importance to us is not that it is the largest structure the universe has ever built. Plenty of larger ones exist. Its importance is that it is the specific structure the Milky Way actually belongs to, discovered using a rigorous, repeatable method that could, in principle, and has since been applied elsewhere, be used to define the true supercluster membership of any galaxy in the observable universe, not just our own. Laniakea was, in effect, a proof of concept for an entirely new way of mapping the largest structures in existence, one that happened to be pointed first at our own address, because that is where the best and most complete galaxy motion data already existed. That proof of concept, however, was not the final word on Laniakea's own extent. Improvements in telescope surveys and distance measurements in the years following the original 2014 paper allowed astronomers to trace galaxy flows even farther out than the original cosmic flows catalogue reached, and those improved measurements would go on to challenge, and partly revise, the very boundary that had made Laniakea's discovery famous in the first place. The 2014 paper that first named and mapped Laniakea was always explicit about one limitation. Its watershed boundary could only be drawn as accurately as the underlying cosmic flows catalogue of galaxy distances and velocities allowed, and that catalogue, however large for its time, still ran out of reliable data at a finite distance in every direction. Beyond that limit, the map simply had nothing more to say, the way a hiking trail map cannot describe terrain past its own printed edge, whether or not that terrain continues. In the years after 2014, Tully's collaboration continued expanding the underlying galaxy velocity catalogue, incorporating new distance measurements for tens of thousands of additional galaxies farther out than the original survey had reached. Applying the same watershed logic to this larger, more complete dataset, a team led by Daniel Pomereed and Tully published new analysis in 2023, suggesting that Laniakea's true boundary, once measured with better data, does not look quite like the relatively confident Beeson outline the original paper had drawn. The newer analysis found that the flow of galaxies near what had been considered Laniakea's outer edge was, in places, weaker and less coherent than the original data suggested, meaning some galaxies previously counted as clearly belonging to Laniakea's basin might, with better measurements, turn out to sit closer to a genuine boundary region, an ambiguous zone where the pull toward the Great Attractor and the pull toward more distant structures like the Shapley concentration are more evenly matched than the 2014 map could resolve. In some directions, the improved data suggested the basin might actually extend somewhat farther than originally mapped. In others, it suggested the original boundary had been drawn slightly too generously. This is worth stating plainly, because it says something important about how this entire body of work actually functions. The 2023 revision did not discover that Laniakea does not exist, or that the original discovery was mistaken. It refined the edges of a real, physically grounded structure using better data, in exactly the way a coastline surveyed with satellite imagery will always look somewhat different, more detailed and less certain at the smallest scale than the same coastline drawn from a ship's early manual soundings, without either version being wrong about the fact that a coast, and a continent behind it, genuinely exists. The deeper reason the boundary keeps resisting a final, precise answer traces back to the watershed method's own core logic. A ridge between two river basins on Earth is, at least in principle, a sharp geographic line because water at any given point flows definitively one way or the other. A ridge between two galaxy flow basins is inherently softer, because the pull each galaxy feels is a sum of contributions from many mass concentrations at many different distances simultaneously, not a single definitive downhill direction the way water experiences under one uniform gravitational field. Near Laniakea's true edge, a galaxy's motion may be responding almost equally to the Great Attractor's pull, and to the more distant tug of Shapley, or other neighbouring basins, making the very question of which supercluster it belongs to genuinely, physically ambiguous, rather than simply hard to measure. Current researchers working on this problem generally treat Laniakea's core, the region including the local group, the Virgo cluster, and the Great Attractor itself, as solidly and confidently established, while treating the precise outer boundary, especially in directions closest to the Shapley concentration, as an active area of ongoing measurement rather than a settled figure. Future surveys, gathering distance and velocity data for still more distant galaxies, are expected to continue refining that edge for years to come, the same way improving instruments have refined the mapped size of the observable universe itself many times over the past century, without ever suggesting the universe was somehow different from what earlier measurements had shown. What has remained stable through every revision, from the original 1980s discovery of the great attractors, pull through the 2014 naming of Laniakea to the 2023 refinement of its edges, is a central fact this entire method was built to establish. Our galaxy is not an isolated island drifting through empty space on its own trajectory. It is one small current within a genuinely vast, genuinely mapped, if imperfectly bounded, river of galaxies, all sliding, however slowly and however temporarily, the same general way. Laniakea did not simply hand astronomers a new name and a bigger number to describe our cosmic address. It confirmed, at a scale directly relevant to the Milky Way, something cosmologists had already suspected from studying the universe's overall structure, that galaxies are not scattered through space at random, but arranged into a connected, three-dimensional pattern of filaments, sheets and clusters separated by enormous nearly empty voids, a pattern astronomers call the cosmic web. Laniakea is in effect one large, well-mapped neighborhood of that web, examined in far more detail than most of the rest of it has ever received. The cosmic web itself is not built primarily out of the galaxies we can see. Ordinary matter, the stars, gas, and dust that make up every galaxy described here, accounts for only roughly 5% of the total mass and energy in the universe. Something on the order of 27% is dark matter, an invisible form of matter detected only through its gravitational effects, which does not emit or absorb light and cannot be observed directly by any telescope. Computer simulations of the early universe, built using dark matter's known gravitational behavior, reproduce the filament and void structure of the cosmic web with striking accuracy, strongly suggesting that dark matter's gravity, accumulated over billions of years, is the actual scaffolding on which structures like Laniakea and the galaxies within them were built in the first place. The remaining roughly 68% of the universe is dark energy, the same poorly understood force responsible for the accelerating expansion that will eventually pull Laniakea apart. Seen this way, the entire outward journey, from the Sun's 8-minute journey of light to Earth, out through the Oort cloud, across the Milky Way's 100,000 light-year disk, past Andromeda and the local group through the Virgo cluster, and finally out to Laniakea's full 500 million light-year basin, is really one continuous story about gravity's reach, and about dark matter's invisible hand in shaping where that gravity's reach could act. Every larger structure examined here exists because gravity, working patiently over roughly 13.8 billion years, pulled matter together at every scale it could, from atoms into stars, stars into galaxies, galaxies into clusters, and clusters into the loose, flowing river we now call Laniakea, before dark energy's accelerating stretch of space finally began to win out at the largest scales of all. It is worth returning briefly to a single pale point of light in the night sky, one star among 100 billion or more, in a galaxy that is itself only one among 100,000 others sharing a single gravitational address. That description could sound, told one way, like a story about insignificance, about how small and how peripheral our position turns out to be at every scale examined. The Sun sits nowhere near the center of the Milky Way. The Milky Way shares its local group leadership with Andromeda rather than dominating it. The local group sits at the outer edge of Virgo's reach, and the entire local sheet occupies an unremarkable outer filament of Laniakea, far from the great attractor's dense core. But there is another way to tell the same story, and it is the one the evidence actually supports. A civilization that exists on one modest planet, orbiting one ordinary star, in one unremarkable spiral arm, managed to build instruments sensitive enough to measure the individual motion of tens of thousands of separate galaxies, compare those measurements against each other, with enough precision to trace the shape of an invisible gravitational landscape spanning 500 million light-years, and use that landscape to correctly identify not just where we are, but which direction we are all, together, actually moving. Nothing about our position required us to be special for that achievement to be possible. It required patience, careful measurement, and several decades of astronomers building on each other's work, one galaxy's velocity at a time. Laniakea will not last forever, and in the deepest sense, it never fully existed as a bound permanent thing in the first place. It was always a pattern of shared motion, destined to loosen and eventually dissolve as dark energy continues its accelerating work. But the map itself, the achievement of having measured it at all, belongs to this era of cosmic history in a way nothing can undo. Somewhere within the flowing temporary river of 100,000 galaxies that is Laniakea, on a small blue planet circling an ordinary star, that river was, for one brief window, actually seen and understood by something living inside it. Every galaxy in this vast flow, from the Sun's own modest neighbourhood to the far filaments of Laniakea, sits inside a structure held together not by a solid shape but by a shared direction of motion, 100,000 galaxies quietly falling the same way, down invisible slopes of gravity toward a low point they will never quite reach. That is a strange kind of home. It has no wall, no surface, nothing a traveller could ever cross and know they had left it behind. It is defined only by which way things are moving, and dark energy is already loosening even that. In a few tens of billions of years, the astronomers who study this method predict the galaxies now called Laniakea will stop responding to each other at all, pulled apart faster than gravity can hold them, and the name itself will describe a memory rather than a place. Yet none of that dissolution is a tragedy of scale, or a reason to feel smaller for having a temporary address. It is instead a rare kind of gift. A civilization on one modest planet, orbiting one ordinary star, in one unremarkable arm of one galaxy among 100,000, has managed to look outward far enough and patiently enough to measure the shape of the river it is standing in. Very few things in the universe ever get to know where they live. For a brief cosmic moment, we do.